All right, so far this unit, we've talked about the mole and how it's related to different relationships we know, right? 1 mole equals 602 sectillion particles, which we write in short as 6.02 E23, right? That's 1 mole, and this is how many particles, atoms, or molecules that we might have. We also know that 1 mole equals the molar mass of a substance. So while 1 mole is always the same amount of particles, those particles may weigh differently, right? So just like we use the comparison 1 dozen. If I have 1 dozen donuts, that's always 12. If I have a dozen cookies, still 12. But those donuts and cookies weigh differently. So a dozen donuts may weigh a little heavier than a dozen cookies, right? So we've looked at that mole to Pam and mole to gram ratio. We're going to look today at what if we have an equation and I want to know how many moles of hydrogen I need to react with oxygen to make water and what that ratio is. We call those mole ratios. So if we look here, we've got the equation for the combustion of methane. And so what this essentially is telling us, as we balanced it last unit, it was really telling us that I have 1 methane for every 2 oxygens, and that's going to produce 1 carbon dioxide for every 2 waters. Right? If we up this ratio, instead of just the most simple 1 to 2 to 1 to 2, we can say I have 1 mole of CH4 for every 2 moles of O2, and that's going to give me 1 mole of carbon dioxide and 2 moles of water, right? Because if I'm actually looking at this as individual particles, like 1 methane and 2 oxygens, I can't go into the lab and just pull out 1 single methane and react it with 2 individual oxygen molecules, right? I can't even see those atoms to then be able to pull them out. So we need more of a measurable quantity. That's why we say it's a mole ratio. 1 to 2 gives us 1 to 2 in this equation. All right, so far as we've looked at the moles and the relationships we know that if I'm going back and forth between moles and grams, I'm going to use the molar mass from the periodic table. If I'm going back and forth between moles and I want to know how many I have, how many particles, how many atoms, how many molecules, then it's equal to 6.02 times 10 to the 23rd, or 602 sectillion particles. So what we're going to talk about today then is your mole ratio. That's the new conversion factor we're looking at. The only thing you need to use for this would be your coefficients in a balanced equation, because your coefficients, when you balance it, already tell you the mole ratio of what you need, what's produced, what will react together. So let's add to the chart that you have so far. Already we've talked about you have mole, and 1 mole is equivalent to, we know the relationship to Pam, 6.02 E23. And we also know that we can go from moles to grams, which is equivalent to the molar mass. So we're going to add another little stop on our flow chart. This time we're going to go up here and we're going to go to another mole. And this might be moles of substance B. So now we're actually switching substances. Down here at the bottom, this is moles of A. Let me change my color so I can kind of show you what I'm talking about. This down here at the bottom, oh, you can't see yellow. All right, this down here at the bottom is as we're converting back and forth between substance A. All right, how many moles per grams of substance A, or how many moles per PAMs of substance A. This up here at the top, we're talking about substance B. And as you can assume, we're going to add to this later on. But today we're just going to take this mole bridge. We call this right here the mole bridge. And we are going to go between substance A and substance B. So maybe I'm looking at how much oxygen, how many moles of oxygen do I need to react with 2 moles of hydrogen? All right, so we're switching substances to figure out what we need in the lab. This is important so that we don't have a bunch of excess, right? As pharmacists are making your medicine or other chemical compounds that are going into like household cleaners and things like that, if they are not using the correct mole ratios for what's going to react, then you end up with a completely different type of medicine, or you end up with excess of something that isn't good for your body, and pieces like that. So that's why mole to mole is really important in chemistry, looking at, we also don't want to waste our reactants, right, or end up with a bunch that's left over. So we're looking at our mole to mole ratio. Now, as you have written your 1 and 6.02 E23 and all your conversion factors for the bottom, your conversion factor here is your coefficients. So go ahead and add that to your flow chart in your notes there where it says let's add or updated conversion flow chart. All right, we're looking at going from moles A to moles B using your coefficients in a balanced equation. So let's look at this first example here. It says how many moles of carbon dioxide are produced from the combustion of 12 moles of ethanol? The reaction below. All right, so just like before, you're going to start by identifying your given and your find. So they gave us 12 moles of ethanol. That's our G given. And they want us to find moles of carbon dioxide. So if you look at your little map, and I gave you a copy of the relationships you know down here in the bottom right corner. All right, we are starting at moles of ethanol, moles of substance A, and we are trying to go to moles of substance B, which is our carbon dioxide. So you're going to start this just like you did all the problems from the last two lessons. You're going to start with your given. We don't know where we're going if we don't know what we're starting with, right? So 12 moles of ethanol, C2H5OH. If you want to write the word ethanol, that's fine too, as long as you have it there. And just like the last few lessons, you start by canceling out what you have. We don't want moles, we want to leave moles. So we're going to drop it to the bottom. Whatever comes up must come down. So moles of C2H5OH. Now when I cancel this mole here on the bottom, right, I am then going to moles of B at the top, right? Here's the options I have. I can go to Pam's, grams, or moles. Well, the route we want to take is to the top. All right, so I'm canceling the moles that I have, and I am going to moles of substance B, which is our carbon dioxide, CO2. Now, here's what's really important. So far, we've been putting 1 as the base of moles, and it is in terms of grams and pams. For every 1 mole, there's 602 sectillion. For every 1 mole, there's the molar mass. But when we're looking at this mole-to-mole ratio, right, I always want you to either box or highlight whenever you see mole over mole. That means that you are taking this path on your conversion chart. So you need to use coefficients here. This is not the number 1. We are looking at coefficients. So box in right here where you see mole over mole on your problem. That means that we need to go up here and we need to find the coefficient of CO2, which is the number 2. So I plug in our 2. And then we need to go find the coefficient of ethanol, which we see here as, oh, there's no number. Well, what does that mean? That's an invisible 1, just like in math, there's a 1 before an X. So we put the 1 there. So we plugged in the coefficients as our conversion factor. All right, we know the mole-to-mole ratio. So just like you've been doing, we're going to multiply across the top. 12 times 2, bring over the bottom. So 12 times 2 is 24. Divided by 1, I have 24 moles of carbon dioxide. That's your final answer. So if anything, this is really almost simpler than what you've been doing. We're just looking at the mole-to-mole ratio. So remembering that you've got to use your coefficients for your conversions. Now, as always, I'll start with the easier problems and then I'll add on a few more steps because you all know how to balance and write equations. So that's your first example. Let's take a look at the second problem here. This one says how many moles of a hydrogen are needed to completely react with 2 moles of nitrogen? So again, if you'll just focus in on what is it asking us to find and what did they give us, all the wordiness of the problem goes away. So they gave us 2 moles of nitrogen and they're asking us to find moles of hydrogen. So here we are in our little path, right? The relationships that we know. We are at moles of substance A and they're asking us to find moles of another substance, which means here's the path we're following. That means that we need to use our coefficients. So on the last problem, I gave you a balanced equation. You need to make sure that I gave you a balanced equation here so that you can use your coefficients. And if we look, is this equation balanced? No, I have 2 nitrogens here and only 1 over here. So we need to balance that. I'm going to do that quickly for you. If you're not sure how to balance, go back and watch that balancing video. All right, but I have 2 nitrogens here. I only have 1 here, so I'm going to put a 2 in front, which means I now have my 2 nitrogens. Good, we fixed that. But now I have 6 hydrogens. Right, 2 times 3. So that means I need to go over here and put a 3 so that my hydrogens are now balanced. Now that I have a balanced equation, we can use these coefficients to do our conversion. So as always, start with your given, which is right here, right? 2 moles of nitrogen, which is our N2. And it says how many moles of hydrogen. So we're going to cancel out that moles of nitrogen, MOL, of N2, cancel moles of nitrogen, and we are going to moles of hydrogen. So remember, whenever you see this mole to mole ratio, that means you're using coefficients. I would box that in as you're doing these problems. This is why I always encourage you to fill out your units before you plug in numbers so that you don't accidentally go and put 1 here, because it's not a 1-to-1 ratio necessarily, right? That 1 only works when we're looking at particles in grams. Mole to mole means we have to use these coefficients. So we're going to go up and we're going to find H2, hydrogen. The coefficient is 3. So I'm going to plug in 3 for H2. And then it says, what about N2? So we're going to go find N2. Well, there's no number in front of it because it's an imaginary 1. Remember, like your 1 and 1x. So I'm going to plug in a 1 down here. That is a 1 because the coefficient for N2 is 1. And we can check that, yep, we have canceled moles. We're now at moles of hydrogen. As always here, we're going to multiply across the top, multiply across the bottom, bring them over. But 2 times 3 is 6 over 1. Well, 6 divided by 1 is 6 moles of H2. That's what we're being asked to find, moles of hydrogen. All right, let's look at the next example. This one says, how many moles of oxygen are produced by the decomposition of 6 moles of potassium chlorate? So here is my given, 6 moles potassium chlorate, and here is my find, moles of oxygen. So we're down here at moles, trying to go to your other mole. So this is the path that we're taking. Now, as I set this up, remember, you need to have coefficients in order to do your mole to mole ratio. So is this equation balanced? Well, we see right here I have 3 oxygens and 2 oxygens. So no, it's not balanced. Let's go ahead and do that. Again, I'm going to do it quickly for you. If you need review on balancing, go back and watch that video. 3 on the left, 2 on the right. So we're going to make these 6 to have that in common. Right? That means I need a 3 in front of that oxygen and a 2 here. Well, that also changes my potassium and my chlorine. So I'm going to put a 2 in front of KCl. And so now I have 2 potassiums on the right, 2 chlorines on the left, 2 chlorines on the right, and 6 oxygens on the left, 6 oxygens on the right. So we're balanced. Let's go ahead and do this problem. It says we have 6 moles of potassium chlorate. And the nice thing, since you have a formula here, it's already written there for you. You know what the formula of potassium chlorate is. So set it up as always. We're going to cancel this out, moles of KClO3. And when I leave moles of KClO3, I'm trying to go to moles of oxygen. All right, so moles of O2. We canceled moles, go into the other mole. And now, again, here you see your mole to mole ratio. When you see this, box it in so that you remember, I need to go find my coefficients. So let's look for those. We have oxygen. Whoops, that's the eraser, not the highlighter. We have oxygen. So let's go find oxygen. The coefficient for that is 3. Then it says KClO3. Well, the coefficient for KClO3 is 2. And solve. Right? You can see here your moles of KClO3 cancel. And so then you're going to multiply across the top, multiply across the bottom, bring it over, and divide. So 6 times 3 is 18, and then divided by 2. So we have 9 moles of oxygen is our final answer. All right, so we're going to step it up a little bit here. As I shared with you, I'll always start with the easier problems, and then we'll add some more pieces to it. We are doing the same process here. There's just a few extra steps that are involved. All right, so it says how many moles of chlorine are produced from the reaction of 3 moles of fluorine with an excess of sodium chloride. I'm going from moles to moles of 2 different substances, right? I'm given fluorine. They're asking me to find moles of chlorine. In order to do that, I need coefficients, which means I need a reaction, an equation. So if you look here, this is just interpreting your equations just like you did last unit, all right? We need to figure out what are our reactants and what are our products. So what is reacting? It says the reaction of fluorine with excess sodium chloride. Now, when you see the word excess, don't worry about it. It just means you have a lot of it. So it's kind of like if you went in the kitchen and you say, I have only 1 box of flour, but I've got a dozen eggs, right? You've got a lot of eggs. You have excess eggs, but you just have a little bit of flour. So that's essentially what this is telling you. So your reactants here, if we look at what it's given us, our reactants are fluorine. Fluorine by itself is F2 with, that's a plus sign, so plus sodium chloride, NaCl. And this is a single replacement reaction. You all know what this is, but if not, you can also look back at your equation here, and it says how many moles of chlorine are produced. So that helps you see what that one product is going to be. It's going to give you Cl, but we know that that has to have something else, right? Where did our Na and our F go? So that's our single replacement reaction, where you have your fluorine and your chlorine are switching. So Cl plus NaF. Na was +1, F was -1, so it just ends up NaF. All right, so you've wrote your equation. Let's make sure it's balanced because I need to use coefficients, which means I need a balanced equation. So we have 2 fluorines on the left, but only 1 on the right. So that means, make it a different color here, I need a 2 in front of here. Well, I fixed fluorine, but now I messed up sodium. I have 2 sodiums on the right, but only 1 on the left, so we're going to put a 2 here. Right? And that fixes everything. If you look, we've got 2 fluorines, 2 sodiums, 2 sodiums, and 2 chlorines, 2 chlorines. So, again, nothing new here. It's just involving the steps that you used last unit. To reiterate, in case some of you were wondering, where in the world did we get all of this from? It said the reaction of fluorine with excess sodium chloride. So if you see there in yellow, I've highlighted in yellow in words and in the formula, the equation, what you got. And then it says how many moles of chlorine are produced, right? Well, it's a single replacement reaction. We know that NaF can't just disappear, all right? So single replacement there. Now that you've written and balanced your equation, we can do the conversion it's asking us for. This is why it's really helpful if you have identified your given and your find. Otherwise, you are going back and interpreting this problem multiple times, and it can seem overwhelming, lots of words, and confusing. So this is why it's really helpful where I gave you that spot in your notes to identify given and find. So we don't have to go back and really read this again. We know that we're given 3 moles of fluorine. Same as always, we're going to cancel that out and put it at the bottom, moles of fluorine. And it wants us to go to moles of chlorine. And I can go straight there from moles of A to moles of B. Here is that mole to mole that you see. So when you see mole to mole, remember, you have got to use those coefficients. So we're going to go find chlorine. Chlorine's right here. Oh, it only has a 1 in front of it. Right, imaginary 1. And then it says fluorine. So we're going to go find fluorine. Right here. Oh, it has a 1 in front of it. That's why you don't see it. Now, these are 1s because that is what the coefficient is, not because that's the base of mole. It is a mole to mole, mole over mole, so we had to use coefficients. Right? And so we just solve. You see here, moles cancel, and we're left with moles of chlorine. And so then 3 times 1 is 3, divided by 1 gives us 3 moles of chlorine. All right, and so that is how you do molar ratios or mole-to-mole conversions. Again, the only added pieces that you may see is making sure that you have an equation and making sure that that equation is balanced. Other than that, these conversions themselves, as you see right here, are very simple. Just make sure that you are always using your coefficients when you see a mole-to-mole ratio, as you see right here, because it tells you you're conversion factor. And the relationship we know between those moles is that mole to mole ratio.